Let's start chapter number 2 next, which is on inverse trigonometric functions. Let's start with our familiar sine function. We already know that the sine function has the entire set of real numbers as its domain and this closed interval as its range, where the left endpoint is -1 and the right endpoint is 1. And you also know that the graph of the sine function looks like this. Here you are looking only at a bounded portion of the graph. The graph extends on either side of the y-axis indefinitely. There is no end to how far the graph goes on that side and also on this side. So let's see the graph once more. Actually, we are going to see something about this graph, something very specific. Namely that this function is not one-to-one, not a one-one function, which actually we already know, but we can also see that from the graph. For example, you can already see that there are many points, many real numbers at which the sine function becomes 0. For example, when x is 0, sine x is 0, so the graph passes through the origin. Also, when x is pi, when your input is pi, then also sine is 0, sine pi is 0. Similarly, sine of minus pi is 0. In fact, you already know that sine of any integer multiple of pi is 0. So that means all those inputs are giving you a single output which is 0. So obviously the function is not 1, 1. And as such, it does not have a traditional inverse. Or to put it simply, it just does not have an inverse. It is onto, however. If you choose any point y from here, any real number from this interval, then there exists at least one real number x such that sine x is equal to y. And actually there will be infinitely many such real numbers. Y, this is y. You have chosen a point y in this interval, then there exists at least one real number x such that sine of x is equal to y. But then this also happens for any integer n sine of 2n pi plus x, which if you expand using the sine a plus b formula, you will see that you are getting sine x, which is again y. So there are infinitely many real number inputs for which the output is y. So the function is not one-to-one, but it is onto. But we already know from our knowledge of inverse functions that only one-one and onto functions, that is only bijective functions, have inverses. So our sine in this ordinary form does not have inverse. But can we do something to the function so that it becomes 1, 1 and so that that modification has an inverse? We can do this, for example. We keep the function intact. Function intact means we do not change the rule of the function. It is still the sine function. We also do not change the range, but we change the domain. Or to put it more accurately, we are restricting the function to this interval. We are no longer allowing it to be defined on the entire real line, but rather only on this interval, where the left endpoint is minus pi divided by 2 and the right endpoint is pi divided by 2. So now if you think of the graph also, then the graph also is only this much. That means it will start at this bottom point and it will go like this and it will end here. And in doing so, it is actually assuming all values between -1 and 1. So you are actually getting every point of this interval as an output, but which you were already getting there also. But at the same time, now this restriction, this new function, modified function is 1, 1. You no longer have that thing, which you can, there is no need to go through the actual function itself. You can see it much more easily in the graph itself. how to see one-oneness when you are looking at a graph. What was the problem that we were having with this function, that it was not 1, 1? If you try to think of it in geometrical terms, you think of any horizontal line, a line parallel to the x-axis, or you can think of the x-axis itself and see how many times that axis intersects the graph. That is lack of one-oneness, which just means that, for example, choosing the x-axis means choosing the output value 0. For that 0 output value, you have many inputs, 0, pi, on that side 2 pi, 3 pi, 4 pi, like that it keeps going. On that side also minus pi, minus 2 pi, all the negative integer multiples of pi. So if your line, instead of being just this axis, if it slides a little like this, you will get other y values, other outputs, but corresponding to each such y, there are infinitely many points where this line is intersecting the graph. They correspond to inputs, infinitely many inputs for that single output. We don't want that, because that is what is causing this function to be not 1, 1. So that is why we have removed those parts and we only have this part. Now if you think of that part only, okay, which lies between this particle line and this particle line, then it is this. That's the graph of this restriction. For that graph, if you think of a horizontal line and you slide it down, say starting from 1, you slide it down till you reach this level, and see how many times that line intersects this restricted curve. Only once. Corresponding to a y value, there is only one x value for which that y is the output. That is why, unlike this function, this is 1, 1, and still it retains the ontoness. This is a 1, 1 onto function, and that is why it will have an inverse. This is not the only way of doing this though. There are other intervals also which you can consider here. Another such function is this, another such restriction, where this time we consider this interval, which starts at pi divided by 2 and ends at 3 pi divided by 2. So that means for this restriction the graph is this. And this graph, although it does not look like that graph exactly, has those same properties that this one has, namely that this is also onto, graph means I am talking about the function, okay. This is also onto and this is also 1 to 1. If you choose your input x from here, then when your x is pi divided by 2, what is sin x? Sin x is 1. And then as your x moves rightward in this interval and eventually reaches 3 pi divided by 2, your output value decreases and it finally becomes minus 1. But in doing so, it takes on every possible value between 1 and minus 1. And that makes this function also, this restriction also onto, just like that one. And during this journey, every value between 1 and minus 1 is taken on only once. So we get one-oneness also. So just like this restriction, this one also has a traditional inverse. And you can imagine that there will be many others like this, in fact infinitely many. You can continue to go more towards the right. Say next you can consider another such interval which starts at 3 pi divided by 2 and ends at 5 pi divided by 2. So strips or regions on the x-axis like this, they give you these restrictions. You can think of other such intervals on that side as well. For example, another one you can see here itself, where the left end point is minus 3 pi divided by 2 and right end point is pi divided by 2. And the corresponding graph is this, which looks exactly like this one. Okay, so that corresponding restriction also is 1, 1 and onto. So all these restrictions have inverses, although the original entire function does not have a traditional inverse. Now if we write what these inverses are, they look like this. Sine inverse, I mean if you think of the inverse of this function, the domain will be this one, the closed interval minus 1 comma 1, and the range will be this one. The domain and range get swapped when you consider an inverse of a function for which inverse exists. Similarly, the inverse of this function will look like this. So you see that for these inverses, the domain is the same, this closed interval minus 1 comma 1, but the ranges are different. All these inverses of such restrictions are called branches of the sine inverse function. And here this sine inverse is actually not a function in the normal sense, but it is that function which you get simply by considering the entire sine function, for which actually, because that is not 1, 1, this is not a function. In what sense is it not a function? It is not a function in the sense that if you choose any point y from this closed interval, this sine inverse will give you infinitely many outputs, which all are those real numbers whose sine values are equal to that y. So sometimes such relations are called multi-valued functions. It is not a function in the original sense in which we use the word function, but still sometimes it is called a multi-valued function. For that function, these are the branches or its parts, which are legitimate functions. And among these infinitely many branches, that's why I have put here these 3 dots, this specific function is called the principal branch. For the other trigonometric functions also, we have such inverses of their restrictions, where the restriction becomes bijective. They are also, for them also we have principal branches. So now let's look at the principal branches of the other trigonometric functions. The principal branch of the cosine inverse function has this domain, which is the same as the domain of the principal sine inverse, and the range is this closed interval 0 comma pi. This is the principal branch of the inverse tangent function. In this case, the domain is R, because if you remember, for the ordinary tan function, the range is R. Range becomes domain. That fact remains, okay, that fact does not change. And the range here is this open interval minus pi over 2 comma pi over 2. You cannot include these 2 points, however, because the tangent function is undefined at these 2 points. That is why. This is the principal branch of the inverse cotangent function. In this case also, the domain is the entire set of real numbers and the range is this open interval 0 comma pi. Just like here you cannot include these 2 endpoints, here you cannot include 0 or pi, because cot 0 and cot pi are undefined. For the inverse secant function, this is the principal branch, the domain is this difference. From R we remove this open interval minus 1 comma 1, and the range is this closed interval 0 comma pi, from which this single point pi over 2 has been removed. And then we have the cosecant function also. For that also, let's see the inverse. And the principal branch of the inverse cosecant function is this. Here the domain is just like this one, and the range is this closed interval minus pi over 2 comma pi over 2, from which 0 has been removed. This notation COSEC to denote cosecant, that function name, is an outdated one. People nowadays use this one, But of course, our outdated NCERT book does not know that. If you use this one on your exam paper, it's most likely that the examiner won't even know, or whoever is going to evaluate your paper, they won't know what this means. So they will just simply strike it and your marks will be deducted. When we use these symbols, that is sine inverse, we don't see sine inverse here, cos inverse, tan inverse, cot inverse, all these inverse function symbols, the convention is that we mean principal branches. Okay, it's understood if nothing else is said. Now, just like our ordinary trigonometric functions have properties, inverse trigonometric functions also have properties. But let's look at something which comes simply from the fact that they are inverse functions. Namely, when you compose a function and its inverse, you get identity function. This we already know. So that just means these two equations. If you take any point y from this closed interval, which is the domain of the inverse sine function, which means its principal branch, then this is true. Sine of sine inverse of y is equal to y, because their effects can cancel each other. Similarly, if you take any x in this interval, okay, which if you recall is the domain of that restriction of the original sine function, whose inverse is this inverse sine function principal branch. So then for that x, sine inverse of sine x is equal to x, because here also this function and its inverse, they cancel each other and x does not change. And this can be said about the other functions and their principal branches of inverses as well. Next, we have this example where we have been asked to find the principal value of sine inverse of 1 divided by square root of 2. Now, it sounds a little stupid. Let me tell you why. What did I say just now? That whenever we are going to use these names for inverse trigonometric functions, the convention is that we mean principal branches, if nothing else is mentioned. So then why are we again saying principal value of this? It sounds like by this sine inverse we mean that general multivalued function sine inverse, which for a single input is going to give us infinitely many outputs. But from those outputs we have to find the principal value. That means that output which the principal branch gives us. So there is actually no need to write principal value. We could have just simply written like this: find sine inverse of 1 divided by root 2. This means that we want the principal value, and that comes from that convention. But anyway, this is how it's given in the book. So let's now solve it. So we start the solution by naming this something, say y. Then by definition of sine inverse, sine of y will be equal to 1 divided by root 2. Now we know that the range of sine inverse, which sine inverse, the principal branch, is this interval, and pi divided by 4 belongs to this interval, and sine of pi divided by 4 is equal to 1 divided by root 2. So that is why, taking all these things into account, we find that the principal value of this is equal to, I should have written in words, is equal to pi divided by 4. Again, actually there is no need to write this principal value of, but because this is how it appears in the book, so if you don't write this, then marks will be deducted.